are molecular, right? And they had a special name. A molecular compound that will dissociate when placed in water. It's called a what? What's the definition of a molecular compound that will dissociate in water? An acid. An acid. It'll dissociate in water, and the rest of that definition is, and when it dissociates in water, one of its products is H+. Right? An acid. Compound that's molecular in nature, but you put it into water, and it will dissociate, and one of those dissociative products will be the hydrogen ion. So that's what an acid is. Okay? We also talked about some compounds that, when you place them into water, dissociate and release the hydroxide ion, or result in the hydroxide ion. We talked about, well, what are those chemicals called? Bases, right? So again, the definition of a base, chemical that you put into water, and the hydroxide ion results. Hopefully you can see that the hydroxide ion and the hydrogen ion are both pieces of the water molecule, right? If you remove the hydrogen ion from the water molecule, you get the hydroxide ion, and vice versa, right? Okay? So we've talked a little bit about how if you combine an acid and a base, following this model, what will our products be here? H2O and sodium chloride, NaCl. Now, there's the chemical reaction, like this one. Can I write the ionic reaction for this one here? I need to look at everything that would dissociate and write it as ions. Will HCl dissociate when it's placed in water? It will, because it's a strong acid, right? And that brings us to our strong acids. What were our strong acids? Have you guys been writing them by your bed so you always see them in the morning when you wake up? What do we got? HCl, hydrochloric acid. HClO4. Anybody remember that name? HClO4. Let's name that. Is it a binary acid or an oxyacid? It's an oxyacid. How do we know it's an oxyacid? It has oxygen. Therefore, it's named like this one, H2SO4. And that one I asked you to memorize as well. Do you remember what that one's called? Nope, this is just sulfuric acid. So that's important to know, because then we're reminded, hey, oxyacids don't follow the hydroblankic model, right? They don't follow the hydroblankic model. They follow just the, look at the polyatomic ion, sulfate, 8 becomes ic, sulfuric acid. Okay? Hydrochloric, what's this one here? It's not hydro, sorry. Perchloric acid. It's the perchlorate ion, all right? Perchloric acid. Any other strong acids that you know? HBr. What else? Okay, nitric acid, HNO3, the nitrate ion, 8 goes to ic, nitric acid. HClO3. What's HI? Hydro what? Hydroiodic acid. Hydroiodic acid. Very good. So, our strong acids are nice to know, because what they do in water is they dissociate completely. They dissociate completely. Okay? So we had a little sidetrack there to talk a little bit about our strong acids. Let me see here if I can find a roll sheet for us. There we go. So HCl is a strong acid, and it will dissociate completely. So to write the ionic compound for HCl, it's that, right? The ionic equation, right? And again, how did I know to dissociate it like that? Because it's a strong acid. When we say a strong acid, what does that mean? Or a strong electrolyte, what is the strength referring to? Yes, the degree of dissociation. Okay, so is sodium hydroxide going to completely dissociate or no? Yes, it contains a sodium ion. Sodium ions always dissociate. Rule 1. All right, so I can write that as a dissociated compound as well. All right, water, does it dissociate? No, it doesn't dissociate. Water is an interesting thing. Based on its chemical formula, H2O, you might say that it's an acid, right? Because it starts with a hydrogen, and that's one clue that will help us know whether or not a compound is a hydrogen or an acid. And in a way, we'll find out in, not until Chem 106, that it is an acid. It does dissociate, but such a small amount. So it's a really weak, really, really weak. It's the weakest of weak acids. Okay, so because it's weak, we don't show it dissociating. Sodium chloride, will it dissociate? Yes. Na plus, Cl minus. What are our spectator ions here? All right, the sodium ion and the chloride ion. Okay? So, we have been practicing predicting how compounds will dissociate when in water, right? And that's important because if you don't recognize that a specific ionic compound that's aqueous is actually its ions and not the compound itself, then you'll miss out and misunderstand the chemistry that's occurring. And one other thing that we want you guys to be familiar with is how we could describe something like an acid, how it dissociates. And we said that dissociative model is something we should be familiar with, right? This is like HCl dissociating into hydrogen ions and chloride ions. But that there is another way that the book wants you to be aware of, right? Where we include a water molecule and show that hydrogen ion kind of piggybacking on that water molecule. Correct? So we wanted to make sure you were familiar with these and recognize that that's basically saying the exact same thing. We also needed to be familiar with how bases dissociate, right? And this is nothing surprising here. These ions just dissociate, right? There's no helpful place to put a water molecule. In my opinion, this isn't terribly helpful either. This doesn't help you visualize anything better than recognizing that the proton is dissociated with a bunch of other water molecules around it, but it's something that, again, people get excited about, so they want you to see. The other component here, though, where water molecules interacting with bases is important, is when you have some chemical that has a nitrogen on it, right? And they'll usually say this is acting as a weak base, and they'll want you to show how this interacts with water, what it does when it's placed in solution. And of all of these, this is pretty straightforward to me. Does it look straightforward to you? Just an acid that dissociates. Going from this to this is not a big whoop for me because you're just adding a water molecule, right? Is that okay? It may be a little questionable why we need to understand that, but hopefully you'll gather that. This is also pretty straightforward. Soluble compound, solubility rules, right? That's how it would dissociate when placed in water. But this weak base one is the one that's a little bit tricky. And really all of these are kind of to prepare us to recognize how a weak base performs in water. If this is a base and it's going to combine with water, what does the product have to be? What did we say? Has to be hydroxide ion. That's the definition of a base. Something that you put into water and the hydroxide ion results. This doesn't have a hydroxide ion on it. So where is this hydroxide ion coming from? It's coming from the water. What does this do to get that hydroxide ion? It pulls a what? A hydrogen away. Rn, there's the hydrogen. What else do I need to put on here? A plus, because it didn't pull away the electrons, it just pulled away the hydrogen ion. And that leaves behind the positive charge on that species. Okay? So, I think this has kind of caught us up to where we were last time, and hopefully you can see how these, which we were kind of trying to go over, and we started throwing in just some regular compounds and to review, and I think everybody got confused about why we were doing all of this. Okay, so hopefully you can get a little bit of a framework and see what we're doing, and now we're going to move into, again, well, I kind of think we did talk about this, but I don't know how well it was sticking. But moving forward, we're going to be given reactants, like these two, for example. And the question is going to be, will these two chemicals react with each other? Will a reaction occur when I mix these two chemicals together? Now, if I mix something like sodium chloride and potassium nitrate, sodium chloride and potassium nitrate, and I ask, is this a chemical reaction? Is this a chemical reaction? Following our pattern, I just erased it over there, A, B, C, D, that business. What are our products? Sodium nitrate, potassium chloride. Very good. And the question is this actual chemistry? Or are we just mixing them and everybody is a spectator ion? Right? Because we know that when we do mix these solutions together, sometimes you get spectator ions. So, how can we tell? Does this dissociate when it's placed in water? Yes. It contains sodium. How about this one? Yes, contains potassium. Both of these dissociate. I'll draw them out for us so we can visualize it. So, they're all contained in one container. Does this dissociate when it's placed in water? Yes, it contains sodium. Does this dissociate when it's contained in water? Yes. Potassium ion. So what does that tell us? No reaction, right? Nothing's happening. All this on the left is the same as all that on the right. Okay? So that's an example of a reaction. There's no chemistry that occurs. We're just throwing all these things in the same container. But that's not what chemistry is about, right? Chemistry is a change of some sort. So you have to be able to predict the products and see if there's actually a change. When I combine these, why will there be chemistry? What's the product that actually results in a chemical change? Water, that's right. The hydrogen finds the hydroxide ion and forms water, and that can't split up again. They're stuck together. Do you remember what the net ionic equation was for this one? The sodium ion and the chloride ion end up being spectator ions, right? But this is the actual chemistry that's occurring when I combine these two mixtures together. All right? So when you combine an acid and a base, water is a product, therefore it's going to drive a chemical reaction. All right? There are also reactions where a gas is formed. We're not going to focus on that much because it's kind of on the fringes, but it is also a way that chemical reactions can occur. So let's move forward now to some problems. Did we already do this one? 47? So here we want to predict the products, and we also want to predict if a reaction actually occurs, and what's the evidence that the reaction is occurring. Okay? Okay, go for it. 47, predict the products, and how do you know whether or not chemistry is occurring or if these things are just mixing together, right? Go for it. Use your neighbor for help. Well, all we have to do is find out what the ion is here. Can you tell what the ion is there? It's lead, right?
Right.
What's the charge on the ion?
Um, is it positive? Positive one?
Positive what?
Is it positive one?
1? Well, what's the charge on the nitrate?
It's negative one.
Negative 1. And it looks like there's 2. Am I seeing 2 nitrates
so
on
this
there?
is probably positive.
So lead's a positive 2.
Okay.
So lead's going to come over here, and it's going to interact with the hydroxide ion. What's the charge on the hydroxide ion?
It's -1.
-1. So I'm going to need 2 hydroxide ions for 1 PB.
And then,
Not PB2. PB has a +2 charge.
right. So it's PbOH.
That's right.
Okay. And then do we write the charges also?
When you write if you were to have to write the ionic equation,
Okay, but not now then.
well, right now we need to predict the products. After we look at the predicted products, we do have to identify whether or not they're soluble, which is using our solubility rules.
Okay, thank you.
You guys get these? Okay, so what do you got here? Oh, 2 OHs. That's not how you indicate that there's 2 OHs though, right? Just like they did OH with a 2 in it for the calcium ion here.
So when do we do the 2 from that?
That is if you want to show, so right now we're not necessarily, so we're at this phase. We're just drawing the products here. When we want to do the ionic equation for those products, that's when we would do that. You don't need to do that. You could go right into that, but you need to check your solubility rules first then to see if lead hydroxide is soluble or not. Good. Looks good. Very good. So you don't need any charges on these after they come back together like that. Okay? Now you have to predict whether or not one of those is insoluble or not.
Did I do that?
Yes, you did. Very good. Oh, wait. There's one thing. One thing.
2+?
So this was CaOH with a 2 right here, right?
Oh, I totally did not see that.
Okay. And that's also because this is PbNO32. That means this is a Pb with a +2 charge. So you're going to need 2 hydroxide ions. Just like that calcium had a +2 charge, you had 2 hydroxide ions. That lead is going to need to have that sort of a thing around it. Does that make sense? No? Let me see this. See how we have this, the hydroxide's on there, and there's 2. It's because the calcium had a +2 charge here.
Okay.
So this one, the lead ion, had 2 nitrates. Do you know the charge on the nitrate?
1.
-1. That's right. Right? So the lead must be a what here in this case?
2+.
Because it's 2+, that's right. So this is a 2+ in here, so it's going to need 2 of those,
Okay.
right? And when this breaks down, it results in
2.
2 there.
Okay. Okay, thank you.
And this one needs to be fixed as well, right?
So,
You getting it?
yeah.
So you decided that there's no chemistry on that one? Okay, so the products that you predicted were lead hydroxide and calcium nitrate. Now, did you use the solubility rules to determine that they weren't soluble, or they were soluble?
Yes.
Okay, so which rules did you use? Rule 3? Or what? So we're... Oh, really? Rule 3 talks about chlorides, bromides, and iodides, so I'm not seeing those in there right now.
Okay, so, yeah, it was
What does that one say?
all metal hydroxide
Mm-hmm.
and all metal oxides are insoluble,
Insoluble,
Yeah.
except those with
except calcium.
strontium, barium, and then the first one, first row. Okay, column. So that means that, which one's going to be solid?
That one is
Yeah.
insoluble.
Mm-hmm, that's right.
I have a question. So
But there's not chemistry, right? Because you can't really figure out if, like, according to these things, neither of these are soluble.
Insoluble? They're insoluble.
Yeah, insoluble.
If they're
yeah.
insoluble, this is insoluble. Did you decide that that was insoluble or soluble?
Insoluble.
Insoluble.
Both of them.
Insoluble. Based on 5, all metal hydroxides are insoluble. But based on number 2,
Yeah. That's a salt unless.
are soluble, right?
Well, unless it's combined with Ca. That's what it says right there.
Oh, but that's with sulfates? That's rule
Oh,
4?
I thought all salt. I just read
All
salts.
salts containing
So that
that.
one is soluble. So there is
That's right.
chemistry.
Well, I mean, if they're both insoluble, that's still chemistry, right?
Oh.
But here you have one insoluble and one soluble. And that's usually typical. Okay, so we're predicting the products, right? Okay, now, when we predict the products, we need to carry all of our learning from the previous chapters, the previous classes, all. We can't throw it out the window. We have to remember what the charge on our lead ions is, the charge on our calcium ions, right? The charge on our polyatomic ions. What are the theoretical products? We're going to switch partners, right? Calcium, nitrate, and lead hydroxide. Are those right? Do I have them written correctly? Not quite, right? I need to finish them up. What do I have to do to finish them up? Calcium has what kind of a charge? A +2 charge. Okay? There's a couple ways we could have seen that. Here it has a +2 charge because there's 2 of these -1s, also where it's at on the periodic table. So I'm going to need to have 2 of these because nitrate has a -1 charge. How about this? Is that what am I missing here? Yeah, I need a second hydroxide ion. Okay, after I've identified what the products are, again, by looking at the ions and making sure that my combinations are correct, I predict whether or not either one of these is going to be soluble or insoluble, correct? And the solubility rules, do they indicate that this one is insoluble? Is that right? Whereas this one is soluble? Okay? So we weren't asked to write the ionic equation here. But if we were to have written the ionic equation, it would be like this, right? Lead with a +2 charge, and then there's 2 nitrates. Can everybody see how that dissociated from that? Then, calcium with a +2 ion and 2 of these hydroxide ions. This dissociates also because it's soluble. This does not. Lead 2 hydroxide, whoops. So what are my spectator ions? My nitrates and my calciums. And the resulting net ionic equation is lead ion plus 2 hydroxide ions forming lead 2 hydroxide. That's the net ionic equation. Now, we weren't required to go all this way, right? We just wanted to predict the products and see if there's actually chemistry that was occurring. That's all we had to do for this problem. Okay. Anybody start working on the second one yet? Yeah? Who wants more time to work on the second one? Raise your hand. Okay. Predict the products. Use the solubility rules to see if they're insoluble.
Question. So because there's 2 NAs and 2 CLs, it has to be 2 on the side, right? So can we just put a big 2 in front? Okay.
That's the way it has to be.
That's the only thing we can. soluble or,
Is that a 2? That's plus 2.
yeah?
And then there's 2 Cl2, so you gotta put a 2 in front of that chloride ion right there, right? Very good. Does that make sense why we had to do that? Now what do you have here? Is that a plus 3?
So you put 3 in the front?
There's how many? 2, I think, right?
Oh.
So 2 goes in front and it's just a plus 1 charge, right? Sodium has a plus 1 charge. Okay, very good. So you said no chemistry. What are the products over here, though?
It's not one of these polyatomic ions, right?
Mm-hmm.
So you need 2 chlorines to balance out the charges of them.
So the Na2 isn't a thing, right? It's 2 Na plus charges, right? It's 2 of these, yeah. So the 2 goes in front, and there's 2 chloride with a minus charge, and they'll come together to form 2 sodium chlorides,
Wait, they would come together to form 2 of that whole thing.
2 NaCls, right?
Okay,
Because you
yeah.
got 2 chloride ions and 2 sodium ions. Looks good.
I have a question.
So, you didn't really need to, but putting the charges there would bring everything together, right?
Those are both 1.
Plus 1 and minus 1.
And then I have a question for this one. How do I figure, because I know.
How do you what?
I don't know if these are correct. Is that, oh wait.
I think that's right? No, I think, see barium where it's at? It's
Oh, right.
56
Okay,
there,
so
so
it
that's
is
a
2.
plus
Okay,
2.
cool.
And also you can tell by where it was here that it had 2 chloride ions on it, so it was a plus 2. Does that make
But
sense?
then what about this one? Do they each have separate charges or do they have one altogether?
When they come together, right? When ionic compounds come together, then their charges aren't there anymore, right?
Okay, so there's no charge.
Mhm.
Okay.
You're on to the next one already? Good job. Did you say there's no reaction in this one, though?
Yeah.
Well, I don't know. How did you decide that? Look at barium carbonate and sodium chloride. So this isn't going to be Na2Cl2,
Oh.
right? What is it going to be?
I don't know.
It's just like this. It's
Oh, okay.
right?
Yeah.
Because that's how those come together, a sodium ion and a chloride ion. Look for your solubility rules on this one. See if you can see if it's soluble.
With that?
So the barium carbonate is insoluble. Very good. You discovered that, right?
Yeah.
Your solubility rules. Now the rest of the business here, this 2 NAs, you had 2 chloride ions over here, right?
Oh, yeah.
So it just ends up being 2 NaCls, not Na2Cl. If Na and Cl come together or interact with each other, it's going to be NaCl, right? Not Na2Cl. But if there's 2 of them, it's 2 NaCls. You guys getting along? Okay. So what are the predicted products here? Okay. Now, I'm seeing something amongst a lot of people which it makes me want to introduce a slightly different perspective on how to identify the products. If I can see that barium and carbonate are going to come together, I can just write those down like that. And the other ones that are going to come together are what? Sodium and chlorine, right? I can just write them down and look at them before I try to put the coefficients around them or the subscripts. And then think about the ions as they would be and how they would come together. Because I saw a lot of this sort of thing with subscripts down here or something like that, right? So once you see the sodium and the chlorine coming together, you have to remember how they would form some sort of a compound, right? It would be a 1-to-1 ratio. Now, because of what we started with, we see that there are 2 chloride ions and there's 2 sodium ions, right? So you could put that there if you wanted to. And then you would see, oh wait, if those are going to come together, it's going to come together as sodium chloride, and then there would be 2 of them. Right? Barium carbonate, how are those going to come together? I take a peek at my polyatomic ion, I see that, oh, this is a -2. I write it really small because they're going to be coming together, so they're not going to be really there. And this is a +2. And then I see, oh, that's going to be a 1-to-1 ratio. So I can just erase them and say that's the compound that's going to be formed on that side, or on that, in this combination here. Okay? And then I can look at my solubility rules and see that this one is insoluble. Okay? Very good. We're going to skip that 3rd one and we're going to go right to the 4th one. Is that okay? Anybody need more time on the 4th one? So the resulting products are going to be, I can see them, right? Sodium nitrate and calcium chloride, correct? Now we need to make sure that when I write down sodium nitrate, has the right ratio of sodium to nitrate ions, and for calcium chloride, again, the right ratio of calcium to chloride ions. Okay.
I just have a quick question. Because there's two NO3s.
Mm-hmm.
So, do I not put 2 on this side?
Oh, for sodium?
For the NO3s.
NO3s.
Because there are 2 on that side.
There's 2 NO3s here,
Yeah.
and there's 3 NAs there. Huh.
Right, and there's, so
Yeah.
do I
So,
have to
but
balance them?
NaNO3 is not going to have parentheses, right?
Right.
It's just going to be like that. Yeah, you'd have to kind of balance the reaction afterwards.
Okay.
But this one would be mercury phosphate. And the Hg, this is actually a 2. Well, no, you're right. 3 and then a 2. Good, good, you did that
And
right.
then just like balance it out.
Yes.
Okay, thank you.
Like, we have to do the subscripts because we have to balance the charges here, but we don't have to do that here.
That's right. And Na and or sodium and nitrate are both mono charged, right? Singly charged. Monovalent.
But this one,
Which one? The sodium ion?
yeah, doesn't this sodium have 3?
There's 3 of them?
Yeah.
Yeah.
So how come, I guess we just drop those? Like,
Yeah. So, well, I mean, we have to, if we wanted to, I mean, they didn't ask us to balance the equation here, but the equation is not balanced, is it? Right? There's some questions about this equation here. Looks like I need 3 of these over on the right here. And I have 2 of these, so am I going to need a 3 here too? 3 times 2 is 6. So am I going to need 6 of those? So now I have 6 nitrates, 6 nitrates. 6 sodiums, 2 phosphates, 3 of those things, mercury ions. Yeah, so that's balanced. 2, 3, 6, 1. Yeah. What's that? No, you don't need to balance it. All you need to do is to predict the products and determine whether or not they're insoluble or not. So what do we get for this last one? What are our products? Sodium what? Nitrate and calcium chloride. Are either of those insoluble? They're both soluble. So this would be an example where we would say no reaction, no chemistry has occurred. Okay? You're right. It's not balanced. Now, we don't need to balance it to answer this sort of a question, right? Because all we're wondering here is, are there going to be, what are the products here? And you're right, that were the other one's balanced up top? Like the second one's not balanced either, right? We don't have 2 chloride ions on the right and 2 sodium ions on the right. Okay? But you don't need to have to balance it just to predict what the products are and find out if there's going to be chemistry due to a precipitation. So when you mix 2 reactants together and out comes a solid, that's called a precipitation reaction. Right? Okay. So I think that we could probably do this one. We don't need to braid it anymore. We're done there. Let's look at these types of scenarios where now we're mixing acids and bases. A solid isn't forming, but in a way, a liquid's forming, water, right? And that can't go back to the aqueous ions that it came from. So that's kind of like a little bit of a kind of a precipitate in a way. So let's look at this reaction. NaOH combining with HF, and we would like to write the net ionic equation for this reaction. The net ionic equation. All right, now we haven't talked a lot about what to do with weak acids, but we have NaOH, which is what kind of a chemical? A base. Reacting with HF. What kind of a chemical is HF? An acid. Is it a strong acid or a weak acid? It's a weak acid. It's a weak acid. So, when we write the dissociation of the left side, I'll give you a little hint here. The dissociation of the left, sodium ions and hydroxide ions. But HF is a weak acid. It doesn't dissociate significantly, so it won't be written dissociated. Then you can look at the products, find out what the products of this would be, find out which ones of those would be dissociated, get rid of the spectator ions, and find out what the net ionic equation for this reaction would be. Find the products, determine if either of those products would dissociate. What are the products? What is going to happen when we mix our acid and our base here? Okay, you got it?
I think so.
All right. So now, I gave you a little clue that this HF,
Is it going to stay like that?
it stays like that because it's not a strong acid. But this over here, that's right, that will dissociate and that won't. But other than that, you got it, right? So this HF has to come down here as HF still.
So other than that, it stays? So it's like this?
Yep, it stays like that. You can get rid of that plus sign up there by the H.
And then if this is the same?
Almost. You need to have this F minus in there as well. Very good.
Okay.
Because
Wait.
this never was like that, right? It was only HF. So therefore, it was different. It did change, right?
So it separated and then came back together because it's a weak acid?
Because it's a weak acid, it doesn't dissociate significantly, but the base, the hydroxide ion, will still take that hydrogen away and form the water.
But why, it takes away the ion,
The H plus.
but not the H? Or it does?
It did, right? And that's where you have formed water, right?
But didn't it use this H for the water?
Yes.
Oh, no, I get it.
Okay.
Okay, I get it.
Okay, good. How's it coming?
Look, it's gonna be this one. This one, because hydrogen doesn't really, or water doesn't really dissociate well.
Okay, that's right.
Would you separate these two at this stage, or you separate them over here?
So HF doesn't dissociate.